All right, let's start practice problem number 2 associated with sample problem E. This one's going to be another little bit of a mind twist that isn't super complicated, but goodness gracious, it'll mess you up real quick. All right. The student in item 1, okay, so if you don't know who that is, watch the video before this in the playlist. The student in item 1 moves a box up a ramp inclined at 12 degrees with the horizontal. Okay, so that means that we actually have ground, and there actually is a ramp. Okay, there is a ramp. And the ramp is inclined at 12. Gosh darn, I did it again. Oh yeah, it's just 2 sig figs. Okay, oh no, I'm good. I totally meant to do that. 12 degrees. If the box, right, that 35 kilogram box, again, check practice problem 1 if you don't believe me. That 35.0 kilogram box starts at the foot of the ramp and is pulled at an angle of 25.0 degrees with respect to the incline. Okay, so it's yet another. Okay, so again, 25.0 degrees. So this is where your force is being applied. Still being applied with the, so this force is being applied. And we also have the same coefficient of kinetic friction, and we're being asked to calculate the acceleration up the ramp, right? So in practice problem 1, we calculated the acceleration of the box just across the ground, right? Because the direction of the force was up at a 25-degree angle. Now, same box, same force, right? Same angle of the overall force being applied, but now we're walking up a 12-degree ramp. Okay, and so let's see what we can do. Now, first thing I want to do is I want to figure out what forces are acting in the y and x directions for this ramp. Okay, now I'm going to do first. Okay, again, so the forces that are working, in and around the ramp are going to be the force of gravity. So the force of gravity in the y direction is equal to, okay, mg, but it's not being pulled, directly down because again it's at an angle. What we're going to have to do is take into consideration. Let's see, what am I doing? Y. So, because I know the first angle, right, 12 degrees, I'll come back to the other one. And then force of gravity, again, the x direction. Okay, so we can actually crank that out pretty quickly because we actually already have values. Cosine of 12 degrees. Set up my next. Sine of 12 degrees. You know what? I'm just going to break the rules. I'm going to make that 3 significant figures. Break the rules. I'm going to change the question. Because I want to include 3 significant figures here. This comes to be 336 newtons. And then 71.4 newtons. And that might seem weird that there's a force of gravity in the x direction, right? Because gravity works down. But remember, this is an incline. Okay, this is an incline. So gravity is actually causing the object to move to the left, right? So there is going to be a force exerted by gravity in the x direction, right? And it makes sense that it would be less than the force of gravity exerted in the y direction, right? So those numbers do make sense. Now, if you remember our strategy from last practice problem number 1, we're ultimately going to calculate the acceleration by using F equals ma, specifically net in the x direction specifically. We can solve it to get acceleration, but before we can do that, we have to figure out what the net force in the x direction is. In order to solve for the force in the x direction, the net force in the x direction, we're going to need the force of kinetic friction, right? What is actually keeping the box from sliding forward, right, in the positive direction easily? Like what's fighting back against the actual force being applied in the x direction? Okay. Now, hopefully we remember this equation, right? And what that means is, in order to, again, here's my logic. In order to use the second law, I need to have the total net, right, the net force in the x direction. In order to solve for the total force in the net direction, I have to take into consideration the force of kinetic friction. In order to have the force of kinetic friction, I need to calculate the normal force. Okay, I need to calculate the normal force. Whew, sorry, getting a little winded here. So let's start setting up what we need to calculate the normal force. Okay, so my equation that I'm actually going to set up, again, similar to what I use in practice problem 1. Okay, you can watch that. Go back and watch the video right before this. If you want to see me go through it again with a little bit more explanation. Okay, it's going to be the normal force plus the force applied in the y direction minus force of gravity in the y direction. Okay? And so this is actually what I'm dealing with here. Now, this bad boy isn't moving, okay, in the y direction. Okay, it's not moving in the y direction. And so the net force in the y direction is 0. Okay? And what that's going to allow me to do is, when I calculate my force applied in the y direction, okay, I can then calculate, well, I mean, I already did actually, right up here, and I can calculate, got this, I'll calculate this, then I can solve the equation for the normal force. Sorry, my words are a little bit sloppy right now. Okay, let's do that. So that equation, once I rearrange this to solve for normal force, it looks like normal force is equal to F sub g in the y direction, right? The force of gravity in the y direction. Subtract the force applied in the y direction. So I already have this, but I haven't yet. Okay, I haven't done this. So force applied in the y direction. So now we're talking about this force applied in the y direction. Force applied. Now I'm applying force. Force applied in the y direction is going to be equal to the overall force applied, but taking into consideration the angle, right? And so for this, I would go sine, and this would be theta 2, right? The second angle, the 25 degrees that I'm actually pulling the box at. And let's see, that's it, yeah. And so my total force applied is 185 newtons, and then take the sine of the second angle, okay, which is 25 degrees, and then I end up with 78.2 newtons. 78.2 newtons. Let's see. Actually, I might as well do F applied X right now. So I'm not going to use it until later, but I might as well get it out of the way. is equal to F applied, but I got to take into consideration the angle that it's being applied at. So that ends up being same applied force, taking into consideration the 25-degree angle, and that will end up being 168 newtons. So I think those are all the things I'm going to need to plug in here. So going back to normal force. So I have my force in the y direction, and I have my force applied in the y direction. So let's go ahead and calculate that. Gotta remember, 336 newtons minus 78.2 newtons, right? And that'll end up being 258 newtons to the appropriate number of sig figs, right? No places past the decimal is what I'm going for right there. And so my normal force is 258 newtons. Now that I have my normal force, I can plug that up in here. I already have my coefficient of kinetic friction, so I solve for my force of friction, right? Force of kinetic friction. Which is 0.27, and then 258 newtons. And let's see. So I need 2 sig figs there, right? I guess I just go 70. Is that right? 70 newtons. 70 newtons for the force of kinetic friction. Yeah, that should be right. Yeah. Okay, so now we're going to figure out our net force in the x direction. Okay, and it's going to be pretty much, it's going to be very, very similar to this, except it's not going to be equal to 0 because we're going to move the thing. So let's represent it with x. So the net force in the x direction is going to be force applied in the x direction, which I already calculated over here, so I can plug it in now. Minus, and again I had to solve for this. Minus force of kinetic friction. Again, why is it minus? Because the sign of the force of kinetic friction has to be the opposite of the force applied, because friction always operates in the opposite direction of the applied force. Now, I also have to take into consideration the force of gravity operating in the x direction. Remember, the force of gravity is actually making the box want to move backwards to the left in the direction opposite of the applied force. So I actually also have to subtract the force of gravity in the x direction. Okay? Now, once I have this, okay, and again, I already calculated all 3 of these terms. That'll give me my net force in the x direction. Then I can plug that into this equation and solve for a, and I'll be home free. So let's actually see what this, what does this end up being? Where are my notes? Sorry. So I can actually represent this, if I want to, as ma in the x direction, right? Right, because, again, that's this equation. Net force in the x direction is equal to ma, but specifically in the x direction, right? That's what we're looking for. So what I'm going to do here is I'm going to solve. So since these are the same, I'm just going to ignore that part because I already had it represented over here, and I'll go ahead and I'll solve this for a. How about we save some time? So again, so I'll just divide both sides by m. So I end up with, make sure I'm on the camera, acceleration in the x direction is equal to the applied force in the x direction minus the force of kinetic friction minus the force of gravity operating in the x direction, all divided by, what was my mass? 35.0 kilograms. So what are those values? Force applied in the x direction, 168 newtons, minus force of kinetic friction, 70 newtons. Subtract the force of gravity in the x direction. Where did I calculate that? Oh, sorry. 71.4 newtons. Divide all of that by 35.0 kilograms. Whew. And so, again, I'll simplify this. I'll add all those up. All those forces actually end up being 2, right? So the net force is going to be the net force in the x direction ends up being 27 newtons that away, but I have to divide that by 35.0 kilograms, and I end up with 2 sigs, right? So I'll go 0.77 meters per second squared, and it's accelerating up the ramp. Where else would it go? Okay, let's recap. So we have a box being pulled with a force, and the force is being applied at an incline. Okay, but that force is going to occur on an incline itself, on a ramp. Okay, so we have to take into consideration the ramp. So what's the ramp doing? Well, it's changing how gravity is operating on the box and on the box. And so there's going to be 2 different components to gravity now because we're operating at an angle. We're still going to have, a large percentage of the force due to gravity operate in the y direction. Okay, so that makes sense, right? So you still have a lot of force pulling you down, but there's also going to be a force now operating in the x direction, okay, which is basically wanting you to move that way, right? So that's kind of working against your force applied. So we do the force of gravity in both the x and y directions. Now, just to get these things out of the way, sometimes these things are actually really, for me personally, when I solve these, I actually like to do these ahead of time. Like they're the first things I do, right? Figure out how gravity is messing with this. Figure out how the x and y components of the applied forces, right? So I kind of have those terms ready to go. So I can solve for the applied force in the y direction, okay? Applied force in the x direction. So I have those ready to go. Now, again, ultimately I'm trying to get to F is equal to ma, right? The net force in the x direction is equal to mass multiplied by the acceleration in the x direction. And okay, so here starts the problem. In order to solve for force, right, in the x direction, I need to take into consideration, right? I need to take into consideration the forces due to gravity. Okay, that's one of them. Okay, one thing I need to take in consideration. The other thing I need to take in consideration is the force of kinetic friction. Okay, so what I have to do is calculate the force of kinetic friction. But in order to do that, I have to solve for normal force. Okay, now the normal force is a little bit extra fun this go around because there's a force of gravity in the y direction. Well, I mean, there's always force of gravity in the y direction, but it's not just gravity, right? It's not only the force due to gravity. It's the force due to gravity only in the y direction, okay? Only in the y direction, because some of that force is actually operating in the x direction now. Okay, where am I at? Then, okay, subtract the applied force in the y direction. Okay, why do you... and then we get a normal force of, right, so we get our normal force. Now that we have a normal force, we can solve for our force of kinetic friction. Now we can start figuring out all of the pieces that go into our net force in the x direction. So obviously there's going to be the applied force in the x direction, obviously. There's going to be the force of kinetic friction, right, holding the box back. But in this specific problem, because there is an incline, there is some gravity operating in the x direction, and again moving in the opposite direction. Okay, moving in the opposite direction compared to the applied force. So I have to take into consideration all of those. But once I do, that's going to give me net force in the x direction. And then I'll be able to solve for acceleration, and I am hot to try.